So we're now about to enter the last lesson of this rate of reaction unit. This lesson is from chapter 1.7 if you're using the Advantage Chemistry 2 AP textbook. So on to reaction mechanisms. This is pretty much a new topic. It's not something typically that's been discussed in Science 10 or Chem 20 or earlier in an AP course. We're looking at how are we getting from reactants to products. So a mechanism will outline how a reaction takes place. So imagine we have reactants and we turn them into products. I'm being very simple. If A is our reactants, B is our product. Typically, we just write an arrow, reactants go right to products. But we're looking at what's going on here. A maybe turns into something, which turns into something, which finally gets us to B. This part we call the mechanisms, the steps, the process. Mechanisms are not known for all reactions. So very often, we don't know the steps that takes place, and somebody might spend 5 years of their life getting a PhD on and figuring out how a reaction occurs. So as we learn about mechanisms, we're going to talk about them as a series of elementary steps. There might be 2 or 3 steps that lead us from reactants to products. Some of these steps are going to make chemicals that aren't reactants or products. So something made and then consumed in elementary steps are referred to as intermediates. So an example of this, a very simple example, maybe we have some chemical A and chemical B react. Okay. And in the first step, they produce C. And then in the next step, this C that was produced turns into the final product, chemical D. So these are 2 elementary steps. When we sum them up, C is produced in the first step. It's consumed in the second. So we can cancel those out. So our net reaction is A plus B turning into D, where C is that intermediate. Now we're studying kinetics. We've been writing rate laws. The connection between the rate laws that we've been doing so far and these elementary steps is that the slowest step in a reaction, or the slowest elementary step in a reaction, is the one that's going to determine the rate law. So if this first step was the slow step, then we would see 1A and 1B in the rate law. If that first step is the slow one, the second and any other ones would be relatively fast compared to the slow one. Okay, so this would drive our kinetics. So we can take our rate laws that we figure out experimentally and use them to know something about at least one of the steps. So a slightly more complex example. Maybe we have a couple steps. We have A plus B turns into C plus D. This is our first step, so there's a rate constant. I'm going to call that 1 for our first step. And then C reacts with another A, turns into B plus D. This is our second elementary step. I'll call that 2. So I'll just label these 1 and 2 for clear discussion. Our net reaction, we've got A is used up. None of it is ever canceled out. So A is a reactant. We've got B is starting to be used up, but then down here it is consumed. So B isn't an intermediate like discussed before. Something that's put in and then regenerated is actually a catalyst. A plus B makes C, and then C is first made, and then C is used up later. So that is what we've been talking about earlier. First made, then consumed. C fits the definition of an intermediate. So we can nicely see both catalysts and intermediates. They can look the same if you look too fast. It's all about which were they used up first or were they made first. So when we do our canceling to get our net, we've got B was used up and then regenerated. That's our catalyst. C was made and then used up. That's our intermediate. So we're left with 2 A's. We've got a B as a catalyst, so we typically put catalyst above the arrow, and we're going to make 2 and then one more, a third D. Intermediates do not show up in our equations from the beginning to the end. We're not showing the middle. Okay. The rate law would correspond to the slow step. So if this was our slow step, our experimental evidence said we just had A in the slow step, or sorry, we had an A and a B in the slow step, we would know this is slow and this is fast. So assuming that we have some evidence, we know one is slow and B is fast, we can write a rate law for this reaction. So our rate is going to equal K, and it's the first step. So I'm going to call this K1 times the concentration of A. And even though B has been canceled out, B would also affect the rate. Now, when we wrote the rate laws before, we did them experimentally. The coefficients in our balanced chemical equations did not tell us the coefficients, but here they do in elementary steps, the coefficients in the slow step. So there's 1A, so this would be the first power. We typically wouldn't write that, but I want to make that connection. B, there's only 1B, so this would also be to the first order. So first order A, first order B, second order overall is our kinetics. Last a few terms before we move on. The elementary steps could be unimolecular, bimolecular, or termolecular. So in a unimolecular reaction or a unimolecular step, there's only one reactant in the reaction, or we're going to talk about this in terms of steps. Okay, so we might have just A. In a bimolecular reaction, there are 2 reactants in the reaction or the step. So this could be 2 A's or 2 different things, A plus B. So there are 2 things that need to collide in order for this reaction to occur. So unimolecular would have a higher probability. There's no collision. It's just the more A's we have, the faster the reaction will occur. For bimolecular, we have to have this collision. So the more A's or the more A's and B's we have, the faster it'll be. Termolecular, we now need to have 3 reactants in a step or reaction overall. So we could have 3 A's, we could have 2 A's and a B, or you could have 3 different things colliding. Now these type of reactions are less common. The probability of 3 things all colliding at the exact same time to cause a reaction is going to be much lower. And we don't talk about any, 4, 5, 6 molecular type reactions. Sort of connecting these elementary steps to our chemical potential energy diagrams, we'll look at a couple options. So we could have, I'm not going to label the energies on this particular example, so we could have our reactants. We create some products with lower enthalpy. This would be a exothermic reaction because I'm going down. Changing enthalpies down. And we're now going to see these elementary steps in the connection from the beginning to the end. So we might go and have a big hump, and then a second little hump, and then get to our products. And this would kind of follow the previous example. So here we have the rate of reaction of the first step is the slow one. So we'll have the bigger barrier here. The second one is faster, so it must have less of a barrier. And that's what we have in our bumps. The slow step will always be the one with the bigger barrier. The second one has a smaller barrier, and that is our fast step. Our overall activation energy is the energy needed to get over the highest part, okay, the highest activation complex. Okay, there would be two activated complexes, but if you don't have enough energy to get over the highest one, then you don't proceed from the beginning to the end. Okay. So that matches our previous example, just being a little bit more complex with this. We could have, more elementary steps. Okay. Maybe we have a little bump, then a larger bump, and finally a littler hump. So this is going to connect with 3 elementary steps. The first one is going to be relatively fast. The second one is our slow elementary step. And the third one, again, is relatively fast compared to 2. So I'm not comparing 1 versus 3, but just knowing which one is the slow one. And again, our activation energy is from the reactants, the potential energy of reactants up to the max potential energy of the highest activated complex. Looking at a particular example, hydrogen peroxide doesn't decompose very fast. You might have hydrogen peroxide in your medicine cabinet, H2O2. It's quite stable for months to years. But if you add in potassium iodide or anything with iodide, I-, this will decompose fairly instantaneously, and the reaction can be done in much less than a minute. The rate law for this reaction, the rate is a constant times the concentration of peroxide and the concentration of the iodide, which is the catalyst. So catalyst can show up in rate laws. We saw it on the opening slide. If you put in more catalyst, the reaction is going to go faster. That makes sense. So you don't just see reactants. You can even have intermediates show up in rate laws, though that is something we try to avoid writing, and we'll deal with that in the end of this lesson. So the mechanism you would think for this reaction would be just be the peroxide reacting with the iodide as the rate law shows, and it would happen in one step and be all done. That was probably thought for a while that that's what's happened, but it's not. It actually occurs in 2 different steps. The first step is the peroxide reacting with the iodide, kind of as you would expect, but it doesn't go right to the products. It makes iodite minus, and then that reacts in a second step with more hydrogen peroxide, and we end up with our final products that we wanted of water and oxygen. So there is a term that we've already discussed showing up. So we've got this IO-. It is first made, then consumed. So this is a catalyst because it is used up then regenerated. This is an intermediate. Now in this reaction, which one is the slow step and which is the fast step? So we know from our kinetics that's been studied, hydrogen peroxide and iodide must be in the slow step and one of each. So that corresponds only with the first step. So this must be the slow step because it matches our rate law. This must be relatively fast. So our first elementary step would have the bigger activation energy. The second one would be much smaller. So we know this one's slow, so this is going to have a much slower rate a much smaller rate constant than 2, and there's going to be a big difference. If this was like 3 and 4, you're going to see pretty similar rates, but you're likely to see orders of magnitude in difference between the two. Okay. Now this is the lab that my students are going to carry out and determine the rate law. Okay. And when you do that lab, if you're in my class, you're expecting first order for peroxide and first order for iodide. A couple more things to do before we're done the unit and the lesson. Figuring out mechanisms can be really complicated and difficult because we can't see these steps. We see the beginning, we see the end, and you have to kind of use interesting techniques, thinking, knowledge to figure out steps. So one example to kind of just talk about this is photosynthesis. Carbon dioxide and water mixes sugar and oxygen. And you might be wondering, so what's going on here? We've got oxygen all over the place. Does the oxygen from the carbon dioxide end up all by itself in the oxygen as the molecular oxygen, or does the water produce the oxygen? So one way you can actually try to figure this out is to use different isotopes. If you took water and just used a heavier than normal isotope of oxygen, use oxygen 18, not the oxygen 16, that oxygen is almost exclusively. And you see where that oxygen goes. Does it end up in both places? The sugar, the oxygen, both, 50-50 combination. And if you carry out this experiment, you actually find that the oxygen from the water all ends up in the elemental form of oxygen. Okay? And that can lead you to try to figure out what steps are going on. We know for sure that the oxygen that's bonded to the carbon stays with it, and that's where the oxygen in the sugar is coming from. Okay? So you would probably deduce that these bonds are only partially breaking. There's a carbon-oxygen double bond. So we must not be fully breaking all of these bonds. We don't have carbon-oxygen double bonds here, so one of these must be breaking. And you have to come up with little clues, pieces, run tests, get pieces of evidence, figure out what bonds might be breaking, half breaking, double bond, half breaking, and figure out a mechanism. Okay? So we're going to wrap up by figuring out rate laws when there are intermediates, and how do you avoid writing intermediates in rate laws. So the example we're going to do this with is below, and we're just going to do examples where there is a fast equilibrium. This sort of tells us two important pieces. If we have a equilibrium, we're going to assume it's fast, so it is obviously not our slow step. And when you're at equilibrium, the rate of the forward reaction is going to be equal to the rate of the reverse. And this lets us write a rate equivalence for our equilibrium and can help us get rid of the intermediate. So hydrogen plus iodine can react and make 2 hydrogen iodide. All of these are gas phases, but I'm going to leave my states out to speed up the writing. Okay? And it turns out the rate law is a rate constant times the concentration of hydrogen times the concentration of iodide. We kind of get a similar incorrect assumption like you might get with the peroxide and the iodide. You might think this bumps into that. It's bimolecular, and in one step it's all done. But it's actually not. There are two steps, and the rate law that we see that happens to match the stoichiometry of the overall reaction matches one of the slow steps. We actually first have one of those fast equilibrium. The first thing that happens is the molecular iodine turns into two iodine atoms, and this is an equilibrium, so I have that equilibrium arrow. The rate constant, I'm calling K1 for the forward, and going backwards, K minus 1. Okay, this is an equilibrium, and we're going to assume that this is a fast step. The second part to the mechanism is that the hydrogen reacts with this pair of iodine atoms, and that this leads to the final product. If this first step is our fast equilibrium, this must be our slow step, because this is the only other step that's proposed in the mechanism. So overall, let's figure out what the rate law would be using these two steps and see if they match the experimental. If you net these up, we do net up to the reaction. The two iodine atom intermediates cancel out. I'm just not going to write the net. So our rate law, the rate equals the slow step, so that's our second one, so that's going to be K2 times the concentration of hydrogen. There's only one hydrogen, so this is first order. We're not going to bother writing the one. Our second reactant is iodine atoms. There are two of them. And this is where, in elementary steps, the slow step stoichiometry directly connects to our rate law. So this is our rate law. Doesn't match what we're expecting, but the reason it's not matching is we have an intermediate, which is pretty much unmeasurable. So the point of this last slide and the skill you need to develop is how can you do a substitution to get rid of this intermediate? And that's where the fast equilibrium comes in. Okay, we know this is an equilibrium, and we're again assuming it's the fast step. So equilibriums, or at dynamic equilibrium, the rate of the forward, which is I'm going to call 1, is going to equal the rate when it is going backwards. And the backwards is commonly referred to as the -1 version, or minus of whatever the forward one is. If the fast equilibrium was the second step, would have rate 2 equals rate -2. So what is the rate forward for equation 1? So we just have molecular iodine, so this is K1 times the concentration of iodine. The reverse, going backwards, so this is K minus 1, concentration of iodine atoms, and there's two of them, so this is second order kinetics. So we now have an expression with our intermediate in it, and we can solve for the intermediate concentration and plug it in. So that's what I'm going to do. Now, in my isolating, we have iodine atoms squared here. So I am going to just isolate for iodine atoms squared here. I'm not going to drop it right down to just iodine atoms and take the square root, because when I plug it in, I'll just be squaring it right back again. So to get this yellow circle by itself, I need to get rid of K minus 1. So I'll divide this by K minus 1. So we now have an algebraic expression for iodine atoms squared, And I'm going to plug this in. And we're going to have our final rate law. So the rate equals K2, concentration of hydrogen. Now we got our substitution. We got K1, we got K minus 1, and we've got concentration of molecular iodine. That's pretty much what we have for the experimental rate law. Let's just rearrange this a little bit. So the rate equals, let's collect all these K's. We got K1, we got K minus 1, we've got K2, and we've got our concentration of hydrogen and our concentration of iodine, molecular iodine. And that matches our expected rate law. We just know a little bit more about this K value. This lumped in K is not just K2. The rate law is constant. K is a combination of 3 different K values. So that pretty much sums up this unit. Hopefully you can understand first order kinetics, second order kinetics, do all those calculations, half-lives, chemical potential energy diagrams, and then we looked at the middle part of reactions in this slide. So last is one problem for you to work on, and then I'll put up the answer shortly. So can you figure out the rate law? Now the answer is given. We have 2 ozone creating 3 diatomic molecular oxygen atoms. We're given the rate law, but can you figure it out? Here is the proposed mechanism. Please derive the rate law from these 2 elementary steps. Clearly state any assumptions in this derivation, and why would increasing the concentration of oxygen decrease the rate. So in about 10 seconds, I'll start solving this, but again, you should hit pause on the video, see if you can write out, do the assumptions, can you write out the rate law? This is a equilibrium, and can you use that equilibrium to do a substitution to get rid of intermediate? Answer in about 5 seconds. Okay, so let's go through this and see how well you did. Hopefully you got through the math. What might have caused some issues is clearly defining the assumptions. So I'll tackle those first. So we've got 2 steps. One of them is an equilibrium. So I'm going to assume it's not stated that this is a fast equilibrium. So I'm going to assume that step 2 is our slow step that I can start writing the rate law with. I'm just going to label these 1 and 2, and those are the numbers we see under the K's as subscripts. So our rate using the slow step is, so our slow step is K2, and we have a bimolecular reaction, 1 oxygen atom, 1 ozone atom. That is a rate law. It doesn't match the answer because this has a intermediate in it, and we want to use the fast equilibrium to solve for that intermediate and do a substitution. So let's do the fast equilibrium part. So here we have the rate 1 is going to equal the rate minus 1 at equilibrium. At dynamic equilibrium, the rates have to be the same. That is by definition. So K1 times the concentration of ozone equals K minus 1 times the concentration of oxygen atoms. And the most common allotrope of elemental oxygen. We want to isolate this for our intermediate. So I have to get rid of K minus 1, kind of collect our K's together, and I want to get rid of that common allotrope of oxygen. And there we have our isolation. So oxygen atoms is this expression. So let's plug that in. So our rate of reaction equals, so we still have K2. I'm plugging this red circle in, and let's kind of collect our K's. So when I plug the red circle in here, I've got K1 on top, K minus 1 on bottom, and I'm just choosing to put them in numerical order. And then we've got ozone over the common allotrope. And then we've got another ozone. We've got one already, and then we've got a second one. So I'm just going to square this instead of writing it twice. But again, the first one is coming from here. The second one is coming from there. So that's the second one. That's the first one. And our rate law matches what we were supposed to get. So this mechanism does make sense for this reaction. This is just a single K, which would be made up of those Ks in that particular ratio. Last part to this question, explain why the rate decreases. So the rate would go down with increased oxygen concentration. So the rate is proportional to the inverse concentration of molecular oxygen. So as this goes up, this is a denominator, this would cause this ratio to go down, which would cause the rate to go down, which matches that statement. So it's the fact that molecular oxygen, the diatomic oxygen, is a denominator in our rate law, which makes intuitive sense, particularly after studying equilibrium and Le Chatelier's principle. If you put in more product, this might cause the reaction to want to go backwards, or at least inhibit the forwards. Inhibiting the forward would slow down the rate. So hopefully you're able to get through that question. You'll want to practice a few more. So for practice, if you want to take a look at page 91, number 4. Now that first question goes back to the previous lesson, not this one. And then 5 to 8, and then number 12. The left out questions are certainly still good practice, but this should be enough for you to be successful on the quizzes, tests, and ultimately the advanced placement exam. So that concludes our rate of reaction unit. Good luck on your reviewing.